Hello friends, so this is my final project presentation on fatigue analysis of a universal joint. The objective that I decided to go with for this project was to do fatigue analysis and the static structural analysis. I used NCS's static structural module to do this analysis. The material that I went forward with was stainless steel. These joints can also be made of different materials like brass, nickel and all, but I went with the stainless steel material. I used Goodman's mean stress theory to solve this fatigue problem. So, basic geometry of a universal joint. It consists of a center block, two forks, collar pins, connecting pins, shafts, and tibia pins. These constitute the assembly. My initial design had solid edges. These are the material properties that I went with. Initially, I was not able to find the fatigue parameters that are needed to fully define a fatigue analysis, and thus I only went ahead with the static structural analysis and defining the strain, stress, strain, deformations, and safety factor for the joint. Once I was able to do that, I proceeded with the fatigue analysis of my project. These are the stresses and cycles that I obtained to derive the SN curve, mean stress curve, which was needed for fatigue analysis. Here, as you can see, this is a log graph of stress versus number of cycles that each stress corresponds to. So, setup of analysis. While setting up my problem, it's I fixed one end of shaft and gave bending moment of 500 newtons to the second shaft. This was my phase 1 of my project. During the phase 1, the mesh size was pretty coarse, and because of which the results were pretty uh, unreliable. Following are the results that I got from my first phase. The bending moment, as you can see, is pretty low. The total deformation from because of this bending moment is pretty low. The stress is pretty low as well, but compared to the amount of force bending moment that is applied to it, it's pretty good. And the part is still safe because the yield strength of stainless steel is 207 megapascals, and the stress is generated in this component is 171 megapascals. The elastic strain of this part is very less, and it's in terms of zero point 0.0 millimeters, 0.09 millimeters. So I would consider that the part is pretty safe. The safety factor of this part is 1.2, which, considering the ideal conditions, is pretty good. When a person designs the part, it needs to be close to 1.5, but 1.2 is still considered okay. So these were the results that I obtained for my phase 1. For my phase 2, I went ahead with refining my mesh, changing my force as the part was still capable of handling more forces, and to use design of engineering methods to optimize my design. So after optimizing my design, the shaft now is a 45 mm shaft, and the rest are based on it. So because the size of shaft increased, the bending moment that I applied onto my system also increased. Now it's at 750 Newton meter. This is a pretty huge value when compared to the actual application of universal joint. This is my mesh geometry. I went with approximity and curvature method to solve my mesh because it easily accepts the complex curvatures and can easily shape the meshes around the curvatures of a body. I went with this mesh as the edges that were initially straight, like the ones you can see on the fork, have now been given a chamfer to reduce the stress concentrations around it. So after my initial setup, these are the results that I obtained from it. The maximum deformation that you can see is 0.01 mm, which is pretty small. The elastic strain that I obtained out of this analysis is also 0.1% of the actual value. This value is concentrated at a single point. Over here you can see the value and the location where it is concentrated. This location is at the key slot, which in ideal case would be where a person would expect the failure to start. This value is very less. So 1 Mises stresses. 1 Mises stresses are also at the point where the strain was. It's now at 218 megapascals, and as you can see over here it's pretty same. This value is higher than the yield strength of the stainless steel. Because of this, there would be some plastic deformation which would occur when the part is unloaded. This deformation then ultimately leads to the crack propagation and the failure of part, which is then further calculated. So, the mean stress theory. These are the details of the uh, fatigue tool parameters that I decided to go with. I used Goodman's mean stress theory to find out the number of cycles a part would provide without failing. Ideally, if a part is able to go beyond 10 raised to 6 cycles, it is considered to be an infinite life, which is good. But each and every component of a assembly cannot go that much, because after a certain number of cycles, there are bound to be some deformations and damages that are bound to happen. So, life of part. On solving this module, I was able to find that life that the part reached was 4.8 into 10 raised to 5 cycles. This is still a high number, but as you can see, it is concentrated at a small point in the key slot. Uh, as you can see over here, once this starts to break, the crack propagation starts and the load at which this initially happened decreases, and now even with a less load, the part is bound to fail. Safety factor. The safety factor which the fatigue tool gave me is around 1.45, which is pretty close to 1.5, which a person would ideally aim to reach when designing a part which is safe. This this safety factor is considered for the center block and the forks. This is because when these parts fail, when the assembly is in motion, these parts can fly off and hit or injure a person, which is not an acceptable thing. So the safety factor of this part is taken into consideration. So concluding my project, after completing in this project, I believe that design of engineering methods is a better approach when going forward, because physical prototyping and testing of the product is waste of useful resources and the useless results which are obtained from it. The original design was oversized and it was capable of handling more loads than the load it was provided with. The maximum deformation that I got out of it is pretty low, as you can see. This deformation does not this deformation is a plastic deformation and can and uh, lead to failure of part in future. The service life of the universal joint is close to 4.81 into 10 raised to 5 cycles before the crack starts to initiate. This is the number of cycles that a part would ideally reach. The maximum stress is generated for this part are 218 megapascals, which is much lower than the ultimate tensile strength, but it's still higher than the yield strength, and because of which there is a plastic deformation sorry that is generated in the assembly. With all the above results, I believe that the second phase of my project was much more fruitful than the first one, because the mesh was much fine and the load conditions that I defined were eh, pretty good, and because of which the exact place where a one person would expect the crack to initiate is where I got it. Ideally, the crack propagation should start from a key The result I got was a key slot, which is still pretty close by because if a key slot breaks, your key comes out and the shaft does not transmit power. So that's it. Thank you for the project presentation.